Good. Okay, we are recording now. Again, guys, really appreciate if you can turn on your videos and stay with us. It makes a big difference. Okay, good. So we'll pick up from where we left last time, and I think this is really what we talked about at the end of last class. And I hope you had a chance to revisit the last lecture, because if you get that foundation right, like I mentioned in my email, today would be a walk in the park. I'm not sure if the vice versa is also true. If you did not quite catch up on the last one, I'm not sure today it's going to be that hard, but you're going to quickly build up on a bunch of things. Okay. So the high level takeaway from last class was Albert is a vector on 3 dimensions of math, programming, and presentation. And Albert, that vector, is x0, x1, x2. But Albert, the same vector, I mean, and maybe this is how Google recruits their candidates, their interviewees. But maybe SpaceX does it in a different way, where SpaceX says, I'm going to take the same candidate, but I'm going to project it on another basis. And that basis could be machine learning, logic design, and project report. Right? And in that SpaceX's basis, Albert, the same person Albert, becomes Z0, Z1, and Z2. So we can now zoom out and get a global view. We can now say, look, Google and SpaceX are not doing anything different. They're taking the same Albert. One is looking at it in some 3 dimensions of math, programming, presentation. The other is looking at another 3 dimension, but another basis, but both these bases cover the same space, right? R3. Right? So this is the Google basis, this is the SpaceX basis, this is Albert in the Google's basis, this is Albert in the SpaceX basis. Okay? And we said, now if you understand that, which I hope everyone gets now, right? And which I hope many of you might have done 310 and DSP, but you may not have seen it this way. And I feel this way makes it very easy. So now all we need to do is to move from that analogy to a signal, where Albert is no longer a person, but a signal. When that signal is in the time domain, where the axes are T0, T1, T2, then that signal's projection is x0, x1, x2. So that is the signal in the time domain. And I can represent that as the time basis multiplied by the time domain signal, which is exactly x0, x1, x2. Okay. But we said there is another basis which Fourier gave us, and that basis is essentially this. One second. Yeah, that basis is essentially f0. Wait. F0, F1, F2. And what is F0? F0 is nothing but a stick that is not rotating, or a stick that is rotating at frequency 0. Right? So that stick which is not rotating, and this is what I mean by that stick, which is not rotating or rotating at frequency 0, can be written as EJ0, 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 because the stick is at the same location. F1 is a stick that is rotating 1 cycle per n time units. So n is 3 over here. So 1 cycle is e to the power j0, e to the power j theta, e to the power j2 theta. And F2 is spinning 2 cycles in n time units. So a to the power j theta, a to the power j2 theta, a to the power j4 theta. So the SpaceX basis is essentially made up of dimensions that are each rotations, and I can express any signal as a linear combination of rotations at different frequencies. Right? So this is the part that if you get a lot actually. SpaceX earlier was machine learning logic design project report, which means any person who comes to interview, you can express that person as a combination of how much is his score in machine learning, how much is his score in logic design, and how much is his score on project report. Similarly, you can take any signal and express it as a combination of how much is that, how much does that signal, or you can express that signal as a combination of a stick that is not moving, a stick that is moving once per cycle, 1 cycle per n time units, and a stick that is moving 2 cycles per n time units. If that stick is 3-dimensional. If that stick is 100-dimensional, then you can express it as 100 different rotations, one that is not rotating, another one that is rotating one cycle, the other that is rotating 2 cycles, 3 cycles, 4 cycles, 100 cycles per n time units. These are the building blocks for that signal. Again, any signal, this green signal, can be expressed as a sum of a bunch of rotations. Okay? And these rotations individually can be expressed as a vector, where each of these vectors are rotations at integer multiple speeds. Right? So imagine any motion, a leaf on a tree moving. If you think of that signal of that motion, that can be expressed as a bunch of rotations. Imagine your voice signal, which is like a jaggedy signal. It can be expressed as a bunch of rotations. Everything can be expressed as a bunch of rotations. That is the key. It's like these rotations is like your Lego blocks. And given Lego blocks, you can design any architecture, any design, right? It's very similar. These Lego blocks, these rotations form the basis. So any signal in that n-dimensional space can be formed out of these basis vectors, and each of these basis vectors are rotations. I know I'm repeating this over and over again, but whenever you're faced with a problem, whenever you're stuck somewhere, zoom out to the first principles and tell yourself every signal has to be made out of rotations, where the rotations are at increasing frequencies. Okay, if it's an n-dimensional signal, then there has to be n rotations with increasing speeds. Now zoom in from there, from that first principle, zoom in and try to solve problems. Any questions thus far? Good. So then we can write time domain representation as time basis times x0, x1, x2 is Fourier domain basis times Fourier transform, where Fourier transform is Z0, Z1, Z2. Okay, this is basically what we talked about last class. This is the overview. Questions? Great. Okay. Now let's do a little bit of a visualization. Now look, ZM, when we say ZM, what we really mean is this is, okay, wait. This is basically our Fourier transform vector. Okay. So when you take a Fourier transform, your output is this vector. You all agree, right? This is the vector that you get. You take your voice, you give it to MATLAB, and you say, do a DFT on it. The MATLAB will throw out a vector, and that vector is essentially the Z vector. Okay. But remember, this Z0, Z1, Z2, they're all complex numbers. You agree? Because look, these are all complex numbers, and therefore this has to be a complex number, because these are all, for a real signal, this is real. Right? Very good. So if this is a complex number, then how do we visualize it? Okay, one way to visualize is the following. So imagine each of these Zi is essentially Z1 is A1 plus JB1. Z2 is A2 plus J B2 and so forth. Okay. So one way to visualize complex numbers is you take the magnitude and you take the phase. Magnitude is what? The magnitude of Zm is basically a square plus b square square root. Okay. And magnitude of and phase of Zm or angle of Zm is nothing but tan inverse of B2 by A2. This is phase of Z2. All of you with me? Great. So now when you envisioned time domain signal, your axis, your x-axis was time, right? Now your x-axis is frequency. And in your frequency axis, you have m equals 0. That means the stick is not moving. M equals 1. Actually, I got something wrong over here. What did I get wrong over here, guys? This spinning sticks I got wrong. What did I get wrong?
Should the M be moved over by one frequency?
That is exactly right. Okay. M equals 0 means the stick is not moving at all. M equals 1 means the stick is moving fast. M equals 2 means the stick is moving, making 2 cycles, right? So now frequency is in terms of M. And now that whatever the value of Z0 is, the amplitude of Z0, the magnitude of Z0, that is the value here. This is basically square root of A0 square plus B0 square. Whatever that is for M1, for frequency M1, that is the value over here. This is square root of A1 square plus B1 square. This is maybe, and so on. All the way to what is the last frequency? M equals n minus 1. So if you ask MATLAB to show you the graph of the Fourier transform, it will show you two graphs. The first graph will be the amplitude of the magnitude of Zm. And this is what the graph is going to look like. This is what the graph is going to look like. Okay. And for each value of the M, for each frequency, it will show you the magnitude of the corresponding Z value. Make sense? But because if you want to express the Z values, you just cannot talk about magnitude. You also need to talk about the phase, the tan inverse. Right? So what a visualization would also show is another graph where x-axis is frequency, y-axis is phase, and for every value of m equals 0, m equals 1, m equals 2, it will show you what is tan inverse of.
Professor?
Yes.
For the frequency, when you drew it, it goes to the same like area, so it does like a complete revolution. Is that always the case, or is this an example of like frequency steps you're showing?
Say that again.
When you show the frequency, going from like, and then the next one is the same thing, but it goes to full revolution. Is this always the case, or just as an example of a frequency step you're giving?
Okay, let me answer that, bring up that question in very soon, where we will convert this m equals 0, 1, 2 to real frequencies.
Okay.
Okay, just bring up that question over there.
Yeah, okay, no problem.
But for now, I think of it as 0 revolutions, 1 revolution, 2 revolutions, 3 revolution, all the way till n-1 revolution.
Okay.
Right. Okay. So this is what you get when you do a DFT, and I hope these two graphs are very clear to you. Questions thus far? Okay, good. If you are good, then the max frequency of a given signal. Okay, remember this M is the max frequency. When you take a signal and you do its FFT, suppose you see a value over here at M equals n-1. That means that's the max frequency that is contained in that signal. That's the max rotation, right? If instead of this, if there was if this value n equals n was 0, m equals n-1, that means the highest frequency n-1 was 0. Maybe this was 0, but the max value was maybe here, which is m equals n-3. Then the max frequency component would be m equals n-3. And m equals n-2 is 0, m equals n-1 is 0. Then the max frequency component, you would say that the signal has max frequency at m equals n-3. Right? So the max frequency that a signal has is called the bandwidth of that signal. Right? So whenever someone says this signal is of bandwidth 20 megahertz, Wi-Fi signals are of bandwidth 20 megahertz. That means if you take the Wi-Fi signal and you start with 0, the Wi-Fi signal will go up till 20 megahertz. Okay. 5G signals will go up to 1 gigahertz. So that means the 5G signal, if you take it start from 0, the 5G signal will go up till 1000 megahertz, whereas Wi-Fi is only 20 megahertz. Okay. Actually 5G, well, 5G is not really 1 gigahertz, but when someone does 5G in a very high frequency, some version of 5G is supposed to be 1 gigahertz. So that's why there's so much of bandwidth and speed in 5G. But this formalizes this notion of bandwidth, where bandwidth tells you what is the maximum frequency that is contained or that you need to make up that signal. You might need lower frequencies, but the maximum frequency that you need to make that signal is the bandwidth of that signal. Okay. Now, one question is, okay, I get bandwidth, but what does phase mean? Okay. So here is an analogy for what phase means. Remember, we said that these frequency dimensions are like building blocks, are like Lego blocks, right? Given any signal, I can combine these frequency vectors in a way so that I can combine that signal. Okay, because why? Because these frequency vectors form the basis of a n-dimensional space. You give me any vector in that n-dimensional space, I'll be able to make it. We saw that from linear algebra, right? So one way of thinking about this in an analogy, in a metaphorical way, is look, suppose this is the signal that you want. This is the signal that, or this is a shape that you want to build. And you have these two shapes as your building blocks, as your basis shapes. So how will you make this shape from these two shapes? Oh, that's very easy. You just add them. You just fix them side by side. You get this shape by taking this shape and adding it to this shape side by side, and you have this left-hand side shape. Right? That is exactly like saying I have a signal and I combine it by taking some rotation at some frequency and another rotation at another frequency, and I'll get that signal. But now suppose someone says, make this shape out of these two building blocks. Can someone tell me, how can I make this shape by combining these building blocks?
I mean, the picture, you have to move it down. So maybe shift one shape a certain amount.
You have to move it down. That's exactly the right answer. So you exactly move it down to here. Do you agree?
Yeah.
Now, if I add it, it'll exactly become this shape. But look, did I change my basis shapes? I didn't change my basis shapes, right? This basis shape is here. This basis shape is here. My basis shapes are exactly the same. I just moved things, right? Phase, now in the Fourier transform domain, phase is exactly that. So when I want to make a signal, I can start the stick not from the horizontal position. I can start the stick from some other position by giving it a shift of angle and then make it spin at that frequency. Right? So if you think of shapes as frequencies, this is frequency 0, this is frequency 1, and so on. You think of phase as the starting point of that stick. Right? So this is the starting point. Start point of, or start angle maybe. Guys, does that make sense? Questions? Okay, so here's a quick question. Does a time domain signal have phase? Anyone? Does a time domain signal have phase?
Maybe, I don't think so.
Yeah.
You have to convert it to frequency first.
Exactly. What is the meaning of a phase of a time domain signal? There's no meaning. A time domain signal looks like that. There's no notion of a phase. Okay? This notion of phase only becomes relevant once you come to the frequency domain. In the frequency domain, you have sticks spinning at different frequencies and adding up as basis vectors. And you can start the stick from a different angle, starting angle. That's the phase of the frequency. So phase is associated to every frequency, and it's useful in making up the signal that you need. In the same way that these building blocks can be moved around to make up the shape that you need. Okay, question so far? Very good. Okay, so now let's translate things to the real world. Okay, very good. So let's say when a signal is given to you, you sample the signal at a frequency fs, where this is fs. This is the sampling frequency, meaning your ADC, your analog to digital converter, the signal comes in every 1 by fs time, the signal is sampled. The value of the voltage is recorded. Every 1 by fs time, right? So in 1 second, you will get fs samples. That is called the sampling frequency, right? Okay, good. So now look, the slowest frequency that we have done so far essentially is n samples per cycle. You agree? Well, the slowest frequency is 0. Okay, sure. But the second slowest frequency is n samples per cycle. You agree? That's the way, that is this one. The stick was moving theta, 2 theta, 3 theta, so on, till n minus 1 theta. So n samples, actually this should be capital N. Oh yeah, no, this is fine. This is n minus 1 samples gives you 1 cycle. Now sampling frequency is Fs. So now tell me, how much time does n samples take? How much time does one sample, one step take as you move?
Well, definitely not one revolution.
Say that again.
I mean, it's not one revolution like in the previous example you showed for the magnitude. You told me to ask that question again.
Wait, not yet, not yet. I'll come back to your
Okay.
question. Yeah.
Are you just kidding then?
Sure. But answer me this question. N samples
sure.
take how much time? If once the sampling frequency is Fs. So every time if the stick moves, how much time is elapsed? One movement of the stick is how much time?
1 divided by the frequency.
1 divided by Fs. So n samples will take how much time?
N divided by Fs.
Correct. N times 1 by Fs. Okay. So n times 1 by Fs time, actually literally seconds. Right? If Fs is in samples per second. Right? Let's even write that. Sampling frequency Fs is Fs samples per second, which is Fs hertz. Agreed? So n samples take n times 1 by Fs seconds. So how much does one cycle take? One cycle is nothing but n by Fs seconds, right? Because n samples complete one cycle. Guys, is that confusing?
Yeah, that makes sense.
Correct, right? So one cycle takes n by Fs time. Say that again.
Sorry, when you're done, could I ask a question?
Yes, let me just finish this last one. Okay. So if one cycle takes this much seconds, can I ask you the reverse question? How many cycles did you do in 1 second? One cycle takes 10 seconds. How many cycles did you do in 1 second?
Do the inverse of n.
Inverse of n, which is Fs by n cycles per second, which is nothing but Fs by n hertz. So now look, if you sample the signal at Fs samples per second, right? The smallest frequency of rotation that you get, like the slowest frequency that you get, is Fs by n hertz. And then you will get the next frequency. Remember, this is Fs by n hertz. This is twice of that, right? So that will be 2 Fs by n hertz. You agree? Because remember, the number of cycles per second is now integer multiples. Okay. So Fs by n is called the fundamental frequency, and faster frequencies are 2 Fs by n, 3 Fs by n, so on. What is the fastest frequency that you get? Someone? What is the fastest frequency you get here? N minus 1, right? So what is the fastest frequency you'll get here in real frequencies in hertz?
Would it be n minus 1 times Fs over n?
Absolutely. Actually, let me write it that way. You're right. And all of these are in hertz. Okay. So now typically you take pretty large n. N is typically of the order of 1,000, right? So if you take n as 1,000, n samples, that means your pencil is now a 1,000 dimensional vector, right? Your signal is a 1,000 dimensional vector. So if your n is very large, then n minus 1 is almost the same as n, right? Therefore, the bandwidth of the signal, assuming the signal has all these frequencies up till n minus 1 times fs by n, then the bandwidth of the signal is fs. Because when n minus 1 is almost equal to n, then n minus 1 by times fs by n becomes 1 fs. Right? So the bandwidth of the signal pretty much is the sampling bandwidth, sampling frequency that you used. Okay, so summary sentence. I am sampling the signal at fs. That means I have decided the basis vectors for my rotations. And my basis vectors are 0, fs by n, fs by 2n, 2fs by n, 3fs by n, 4fs by n, so on till n minus 1 fs by n, which is pretty much fs for large n. Now ask me all the questions.
So in the first line, it says like, I'm just a little confused on the use of like n. It says like usually we don't define, it says now slowest frequency equals n samples per cycle. Like could you explain that a little more? Like I'm not used to thinking, like usually sampling comes after the frequency that's present in the signal. Here we're thinking of the frequency of a signal in terms of the sampling, which is kind of confusing to me.
Okay, so what I mean by this is, let's see if we can go back to our first very early. You remember this picture we talked about, rotations? Right? We wanted to model rotations. And we said that, look, the stick is in the original starting position. Then the stick goes to theta. Then the stick goes to 2 theta, 3 theta, so on till n minus 1 theta. Right? So imagine old men, old humans, not old men, old humans were trying to model rotation, and the stick is spinning, and it basically takes a picture of the stick or records the position of the stick at this location, then it records it at this location, then it records it at this location, and so on. It's like the human is recording the stick's location. It's as if the human is like an ADC, analog to digital converter. Right? So the stick, so the human is sampling that rotation, right, n times. 0, 1, 2, 3, so on till n minus 1. That is n times, starting with 0 all the way to n minus 1. Now, when the stick is rotating slowly meaning the stick completes one cycle in those n samples, we are calling that the base frequency.
So is there a relationship between n and fs then?
No.
Because if we're describing n in terms of the sampling frequency.
No, we're not. We have said that, okay, maybe I should say this now. You pick a value of n. Let's say n is 100. Okay. That means theta is 2 pi by n. You pick n as 100. That means you're saying when the stick moves in the slowest frequency, when the slowest non-zero frequency, I am going to sample it 100. I'm going to take 100 samples. So I'm going to do this. 0, 1, 2, 3, 4, 98, 99. Okay, how much is theta? Theta is 2 pi by 100. Right? So theta is over here 36 degree, 3.6 degrees. You agree?
Yes.
Now you sample the signal. That is a completely independent parameter. You sample the signal at maybe 5,000 hertz.
I guess that's the confusing part. Like I thought we just said that n was samples. So like I'm kind of confused on the difference between n being 100 samples and like fs.
Okay. Let's put it all together. Ask me the question. Lucas, ask me the question again.
Okay,
It's
yeah.
not here after this page. Okay, good. Yeah, maybe after this page should clear it up. Okay. So consider sampling your voice signal at 8,000 hertz and then taking 1,000 point FFT. Okay, so that means Fs equals 8,000 hertz. And let me not write hertz, let me just write that. And N equals 1,000. What does that mean? That means when this voice signal comes, right? In 1 second, I have taken 8,000. Imagine that the red vertical lines that I've drawn for the samples, imagine this is the 8,000th sample, right? That means this whole thing is 1 second. This is time. This is 1 second. And this is the 8,000th sample. Lucas, are you with me?
Yeah, I think it makes more sense now. I didn't realize n is like the actual, I remember it now. It's like the length of the FFT. So it's the same n. Okay, cool. Okay. Thank you.
Okay. So for those who are still struggling with this, you have a signal, you sample it 8,000 times in 1 second. So imagine this is 1 second. You've sampled it 8,000 times and you have 8,000, you have a vector which has 8,000 values. That's your signal. But you decide to only take the first 1,000 samples, which is this window. And that means your signal is now a 1,000 dimensional vector because your n is 1,000. Capital N is 1,000. And you say, this is the part of the signal that I'm going to compute my FFT on. Right? This is called an n-point FFT or 1,000-point FFT in this example. Okay. So n equals 1,000, Fs is 8,000 samples per second, which is 8 kilohertz. Okay. Now, when you take an FFT of that, this is the frequency axis. What should be the maximum frequency over here? What should be the maximum frequency that you can see? What is this value? N minus 1 by n minus 1 times Fs by n, right? Because that's the maximum value. What is this value? Someone? 0. What is this value, guys?
Fs over n.
Fs over n. What is this value?
2 Fs over n, and so on and so forth.
Right? And now when you take the FFT of that signal, you will see, oh, there are some frequencies at Fs by n, some frequencies at 2Fs by n, so on and so forth. Maybe there are some frequencies which do not have any amplitude, any magnitude. And so, oh, sorry. Let me do that. And so on and so forth. Right? So if you put real numbers, let's put real numbers. So this is 0 hertz. This is how much hertz? 8 hertz. This is 16 hertz. So on and so forth till 8,000 hertz. So what we've said is, if you sample your voice signal at 8,000 hertz and you take 1,000-point FFT, then you are going to represent that signal with basis vectors or with basis rotations, where the rotations have frequency 0, 8 hertz, 16 hertz, 24 hertz, 32 hertz, so on, all the way till 8,000 hertz. Things will still become clear with an example, but just stay with me. But I hope this already gives you the separation between Fs and capital N. Okay. Thus, when analyzing a given signal, we have two knobs.
Wait, Professor.
Yeah.
So based off this magnitude thing here, then that window you drew be wrong. Instead of like having that window of 1,000, shouldn't that 1,000 be split in increments of 8 from 0 to the 8,000th sample?
Say that again.
Based off the way you drew in the magnitude, how you go from 0 hertz to 8,000 hertz, so there's like an 8 hertz interval between each frequency. Then for your window, where your purple window above, shouldn't that highlight 0 to 8,000 samples?
No. Okay, this is Anirudh, right? Anirudh, you asked that question?
Yeah.
Okay, so ask me at the end of this page.
Okay.
So when analyzing a given signal, you have two knobs you can control. Okay, two knobs, two things that you can control. One is sampling frequency, Fs. The other is number of points or number of samples you take into your FFT, which is N. This is exactly this. You have a signal, you can sample it fast, which is the Fs, which is one variable, one parameter that you have to choose. And then you have to say, how many samples am I going to take for the FFT? That is the N that you have to choose. Right? So just because you've sampled at 8,000 samples per second does not mean you have to take 8,000 samples. You can take only 1/8 of a second of that signal, which is 1,000 points, 1,000 samples. Okay, hold on. So large Fs means we can see up to large frequency components in that signal. So imagine extraterrestrial creatures sending some signals towards Earth. If you sample that signal at Fs, the maximum frequency that you can see is Fs, whether Fs, all the frequencies up till Fs, whether they are present in that signal or not. If the extraterrestrial guy sends some signal which has super high frequencies, and you don't sample at those super high frequencies, you're not going to see those frequencies. Right? So Fs tells you what is the maximum frequency that you can see in that signal. Now, look at the next thing. N tells you given that you can see up to this frequency fs, you can see only up till fs, n divides that 0 to fs band into buckets, which are also called bins. Basically divides it into n buckets or n bins. Okay. So you can have large fs, but if you choose a small n, that means your large fs will be divided into few buckets. Whereas if you choose a very large n, you have fine resolution, because in that fs, you have divided that fs into very, very small frequencies. So these gaps would be small. Okay, so large n means we have finer frequency resolution, or more frequency bins within 0, fs band. And the width of these frequency buckets is, of course, fs by n.
Can I ask a question?
Yeah, 1 second. Find an analogy, okay? And I think this might help again. You have a camera, okay? The camera has a wide angle lens. The width that you can see, I mean, you're looking at a beautiful waterfall, or you're looking at a beautiful scenario. The width, the amount of the scenario that you can see is determined by the wide angle camera lens, right? But the resolution at which you see that picture is determined by the megapixel of that camera, right? So similarly, fs is how wide angle, fs is equivalent to how wide angle is the lens, and n is equivalent to how many megapixel in your picture. In signals, fs is equivalent to what is the maximum frequency you can see. N tells you in that maximum 0 to fs, how would you like to chop up the frequency buckets? In other words, how much resolution do you have in those, in that frequency domain? Now ask me questions.
So if you look at the first figure in that page,
Mhm.
I guess what was confusing was like when you did the n is equal to 1000,
Mhm.
you only cover like a portion of the signal. But now that you explained what n is in relation to fs, it just seems like n is like a resolution, right?
Correct.
Okay,
Correct.
so it's not just like you're not just taking like a portion of the signal. You're just like assigning a resolution, because that's what it looks like in the first figure.
No,
like
you are taking a portion of the signal. The question is, what is a signal? Anything, any window that you take is your signal.
oh right, because this is a time domain.
Right, it's in the time domain, right? So if you take a larger window while sampling at fs, you're saying that I'm going to look at this signal at much higher resolution. If you take a smaller window, you're saying I'm going to look at that signal at lower resolution. But fs tells you what is the maximum frequency at which you can look at that signal. Right? So imagine now the camera. You buy a camera with wide angle lens. You're saying that I'm going to look at this picture. I'm going to look at the whole White House. Right? At a narrow angle lens, you're not going to be able to look at the whole White House in one picture. Right? So that is your fs, how much you can see. But then if you buy a wide angle lens and a low megapixel camera, you're going to see the whole White House, but it's going to be pixelated.
Okay, so what
But
if
if you increase n, you're going to see the picture with much better resolution.
okay, so what if n was equal to 1 here? Would that mean we're just looking at one frequency, or
Yes, you're going to look all the frequencies from 0 to fs will get averaged into one value.
Okay.
So it's like you're going to look at the White House, but in 1 pixel, right? It's an analogous to that. But more you increase n, you're looking at the same White House with more number of pixels, so you have better resolution. Right? If you reduce fs but increase n, that means you're looking at a narrow part of the White House, maybe the entrance of the White House, but at super high resolution. Questions? I know I see thinking eyebrows on two of you, I think.
I have a quick question.
Yes.
So when we say n is 1,000, we mean the samples, right? 1,000 samples. So
Right.
do we have to take like first 1,000, or we can take the last 1,000 or anything at random?
So in fact, what people would do is they would keep shifting that window of 1,000 samples to look at that. It's like you take a camera and you have your wide angle, your angle. You keep moving the camera on the signal. So you basically move this window. You move this window on the signal and you keep looking at what your signal has at this 1,000 point resolution.
What is that? What is this movement called?
No, this is not called anything. You just take a window of samples and you take an FFT. Then you move the window and you take another FFT. You move the window, then you take another FFT. You move the window, then you take another FFT. So that way you get to see the whole signal with a good resolution.
Okay. Well, I don't know if we were killed this topic to death yet, but could I ask another question really quick?
Please, go ahead.
So this, I get like everything we're saying now. I understand it a lot more. This helped me understand the N. But could I just check my understanding? Is the actual technical reason we're getting more resolution by increasing N, is it because in the time domain, we're actually looking at more of the signal and therefore we're taking like more samples, and so we get a more accurate of like the frequency components?
Exactly.
Okay, thank you.
Exactly. Yeah.
Okay, so I have a quick question then. If magnitude, I still don't understand, like we're moving by increments here by 8 hertz, right? So isn't this magnitude, like, isn't this a graph or not, or this kind of, yeah, like the magnitude representation here, isn't this showing everything from 0 to the 8,000 sample?
No, it's showing from 0 to 8,000 hertz.
Okay.
Because remember, right? We said that the basis of that frequency space is 0, F1, F2, F3, all the way till n-1.
Yeah.
F0, right? n-1, n-1 F1.
Yeah.
So these values are not samples. There are n such values, but they are not the samples. Okay, this is where Anirudh, I would want you to look at this picture and ponder a little bit more. Yeah, remember this one. Each of these, this is the frequency basis. There are n bases, n vectors in that basis. Right?
Yeah.
So yes, there are n vectors, but each of these vectors is not a sample. It's a rotation of different speeds. If this makes sense, then all you need to think about is this F0 is this F0. This F0.
And then that's F1, F2.
F1. Yeah.
Okay.
Those column vectors of the frequency basis are these values
Yeah.
on the frequency domain.
So at smaller frequencies, and we're getting different magnitude lengths.
Yes. That means the signal has some
Okay.
amount of 0 frequency, some amount of 8 hertz, this amount of 16 hertz. And if you take a rotation of 0 hertz,
Mhm.
and then you take a rotation of
Got it. Yeah.
8,000 hertz and 8 hertz and 16 hertz and whatever in these magnitudes.
Yeah.
and
No,
if you
I
add them
understand.
up- If you add them up, you're going to get this.
So basically, like just for a real example, real quick. So what I'm understanding is, let's say if I and my friend were speaking, and someone was trying to understand what was going on and differentiate it. If they were to basically sample that at different frequencies, they could pick apart my voice from that signal, right, and then pick apart my friend's voice from that signal, and that's how they would like discretize that. Is that essentially the purpose of what this could be used for?
We're going to answer that, but what you said would be true if your voice frequencies and your friend's
Is it a-
voice frequencies are different.
Or different? Yeah. I'm just giving. Okay. So yeah, I just wanted to understand then what this was going to. But okay.
So one last thing. So when you take those 1,000, like the first 1,000 points, does that mean you're perfectly able to get back those first 1,000 when you do the Fourier transform and invert it?
Under certain conditions, yes. If you're, this goes into Nyquist. We are going to get to Nyquist. If your sampling frequency is large enough, you can recover those first 1,000.
Okay, so then what I'm struggling to understand is why FS isn't resolution and why N isn't the point of like the field of view. Because for me, it seems like FS seems to be how close you can get back the original image, while N seems like how much of the original image you're looking at, or in this case, frequency.
No. Because FS, once you pick FS, the maximum frequency that you're going to see in the signal is fixed, which is this.
Yes.
Right? So now the only thing that N will give you is you can divide 0 to Fs by N. Right? So if the alien sends you a signal which has 1,000 hertz, and if you sample the signal at 500 hertz, you'll not be able to see the 200 hertz and the 300 hertz components of that alien signal. You can only see up till 500 hertz. But at what resolution will you see? You will see that at the resolution of how many N that you pick. Okay, Utkarsh, I know this takes a while. This takes a while to sink in, but this is where I think you have to go back and ponder. Okay, just ponder on this. I think these will come together. It's not easy. And that's why I mentioned in this class to look back at the previous lecture. And I was joking when I said it's a walk in the park. Okay. This does need you to ponder a little bit, but I'm happy to stay back after class and chat with you.
Yeah. Okay. Yeah, sure.
Thank you. Okay. Maybe these examples would help a little bit. We are going to do 3 quick examples. Okay. Let's start. Let's do DFT of a signal which is cos 2 pi FMT. Okay, what is cos 2 pi FMT? That's like a signal like this, right? Where the number of cycles per second is FM. So we just pull a value for FM. Okay, good. Let's discretize. Actually, this is one you want to pay attention to. I think this will clear up a bunch of things. Okay, maybe not everything, but a bunch of things. So this is an analog signal. It's in time. So when you sample it, the signal becomes Xn, where N is sample number 1, sample number 2, sample number 3, all the way to sample number capital N minus 1. So that sampled signal should be cos 2 pi Fm, and this time t is nothing but N times Ts. This t becomes digitized by N time Ts. What is Ts? Ts is nothing but 1 by Fs. Tell me if this is right, if this makes sense. I'm going to sample at different points, and at different points, my value of Xn should be cos 2 pi Fm. When N is 0, this will be 0. When n is 0, this will be 0. So that is cos 0, which is this value. When n is 1, this is Ts. So that is cos 2 pi Fm Ts. Well, this is Ts. So that gives me this value. So this is x0, x1, x2, so on, just the way we thought we modeled things the first time. So, oops. So this is basically Ts, which is 1 by Fs. Okay. Now you take an endpoint FFT. Okay. What should you get? Let's make this endpoint here. You take an FFT with this window. What should the, now we want to fill up this, we want to fill up this graph and this graph. One is the magnitude and the other is the angle. Anyone has thoughts?
This is going to be a really wild guess, but I'm going to guess. So the amount that each amplitude occurs is pretty equal, except for like one frequency here, right? Or am I not thinking about this correctly?
Tell me. Go ahead. Not bad. Keep going. The magnitude of every frequency will be
about equal, except for the tro of one frequency.
Which frequency?
The very lowest amplitude, or like what is it? Let's see, like 1, 2, 3, 4, 5, 6.
Remember, this is FM.
Oh right. I guess 6 over Fs, or no. It just 0.6 on the graph.
Okay. Adil, I think you are on the roughly on the right track. Okay. But let me say this. Okay. Anytime you're confused, step back and tell any frequency, any signal can be expressed as a combination of bunch of rotations, right? This rotation is like the stick is not rotating. This F1 is the stick is rotating once. This F2 is the stick is rotating twice. Fm is the stick rotating m times. You agree with me? The x-axis essentially is composed of a bunch of faster rotations. Okay. And each of this is a stick that's rotating. Now I ask you, guys, you have to make a signal which is cos 0, cos theta, cos 2 theta, cos 3 theta, so on. And you have these rotating sticks to make up that signal. These rotating sticks are your Lego blocks. And now by combining these rotating sticks, you have to make up that signal. Can you do it? So the observation that you can make is, look, if I take a stick and make it rotate at theta, cos stick at 0, stick at theta, stick at 2 theta, stick at 3 theta, so on. Hey, do you see the connection that cos theta signal is part of my rotation? Why? Because at 0, I have cos 0, which is 1, and my stick is also 1. At theta, my stick's x-axis projection is cos theta, which is what I want. At 2 theta, my stick's x-axis projection is cos 2 theta, which is what I want. So what I want is embedded in my rotation. But my rotation has other values, which is this sine theta. Okay, this is where I'm going to give you the answer and then make you think. The answer to this question is the following. It is going to be 0, 0, 0, 0 all the way until Fm, and again 0, 0, 0 all the way until Fn minus m, and 0, 0, 0, 0. And this one, phase, will be 0, 0, 0, 0, 0 all the way. Okay, this is the answer. Okay, we are going to completely break this, unpack this. But the first question I want you to think is, I have two frequencies, one at Fm and one at Fn minus m. But hey, cos 2 pi Fm NTS, this seems to have only one frequency, Fm. So the question is, why does DFT have two frequency components?
Is this analogous to the
minus-
copies you get in an FFT on both sides of the y-axis?
Say that again.
Is this analogous to the copies you get of a frequency like negative and positive doing an
Why do
FFT?
you get copies? We are exactly going to go towards that, yes, but we'll figure out why we get copies from first principles. Okay, but the question is, from a very intuitive understanding, 10th grade, high school understanding, right? You have Fm as the frequency, but why does the FFT give you some signal at Fm and some signal at Fn minus m? Suppose I told you that this one is also 0. Fn minus m is 0. There's only Fm. Then that would perhaps make sense. Because cos has Fm and this is Fm. But that won't be correct, right? Because what is this? This is nothing but the stick rotating Fm times. Agreed? Fm is nothing but the stick rotating Fm times in n cycles, in n samples. And that rotation of Fn times, which is nothing but that e to the power j theta, e to the power j m theta, e to the power j 2m theta, so on. That is not the same as cos 2 FMS, cos 2 pi Fm NTS. And we will see soon why we need this, okay? So just be patient. So why does DFT have two frequency components? The answer is, note that cos 2 pi Fm NTS is not a rotation. If your FFT answer was only this signal at Fm, that would have meant a rotation of Fm times. But your cos signal is not a rotation. Cos signal is only the x-axis shadow of that rotating stick. This is the difference. Cos x, cos 2 pi Fm NTS is the x-axis shadow of that rotation. But there is also a y-axis shadow that you somehow need to eliminate to only get the x-axis shadow. Right? It's only the x-axis shadow of the rotation. So you make to cos 2 pi FMTS, to make cos 2 pi FMNTS, we need to cancel out the y-axis shadows of the rotating stick. Does that make sense? Okay, if it doesn't, here is it hopefully better. Let's say Fm equals F1. What is F1? The base frequency, one cycle in n time samples. Let's say Fm is F1, or even like in our earlier case, F1 was 8 Hertz. Right? But I would say forget 8 Hertz. Let's just think of it in terms of F1. F1 is one cycle in n samples. So it starts here. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . This is f1. This is time t0. This is time tn minus 1. Guys, are you with me? I need some visuals because it's getting a little bit hairy, right? But it's not. Just stay, okay, and ask questions. So now, for cos 2 pi f1 nts, the FFT is this. Sorry. Yeah. We said at fm and fn minus m, there will be two values at fm and fn minus m. So for f1, it's at f1 and fn minus 1. That's what the FFT is going to be for this cos 2 pi f1 nts, right? Okay, now I think it will help. F1 is nothing but e to the power j0, e to the power j theta, e to the power j2 theta, so on, e to the power jn minus 1 theta. I hope this is like engraved in your head, right? But what do we want? We want cos 0, cos theta, cos 2 theta, so on till cos n minus 1 theta. Because this is this. Makes sense, right? Now, if this FFT only had this value at f1, that would have meant this equals this. But it's not equal to this, right? This rotation is essentially this, where at the initial time we have cos 0, at the next theta we have cos theta, at the next 2 theta we have cos 2 theta, and so forth. So look, this rotation, whatever shadow it has on the x-axis, that shadow is what we really want. But this rotation also has shadows on the y-axis. You agree? But I need to somehow eliminate those. Otherwise, I'm not going to get what I want on my right-hand side. So which means this rotation is not equal to cos 2 pi f1 nts. I hope this is clear. This left-hand side corresponds to this f1, and the right-hand side corresponds to this cos 2 pi f1 nts. There is some similarity in the sense that the x-axis shadow of the left-hand side equals the right-hand side, but they're not the same.
So they would be identical if the equation was cosine plus sine, right? Or
wait. I know it's tempting. Yes, it's tempting over there. Wait. Okay. So the question
It's a quick question.
Yeah, go ahead.
So that imaginary part you were not imaginary. So this y-axis shadow, how does that create an f1 on the right side coming in from the other interval? Like you had the fn minus 1 magnitude showing. So how does that? Are you still relating it right now, or?
I'm still relating it. I'm not done yet.
Okay. All right.
Okay. So all we said was, if you have f1, then that f1 is a rotation, and that rotation has this y-axis shadow and this x-axis shadow. This x-axis shadow is what we need for the signal, but we somehow need to eliminate this y-axis shadow. Right?
Okay. Yeah, I was just wondering, I didn't understand why the y shadow would matter, because I thought since we're only caring about the x shadow, that can happen when you go the other way, right? Like right
Yeah, it will go, it's going in that direction. Yeah.
Okay.
Okay. So the question is, how can we cancel out the y-axis shadow of this rotation? Right? We have e to the power j0. We have e to the power j theta. We have e to the power j2 theta. And we need this, the right-hand side. We need this part. So this is equal to this. So no problem. Right? But this is equal to this. But what do we do with this? So here comes the idea. Imagine we add another stick, which is in this direction. Right? Now, if we add these two sticks, this stick and this stick, what happens? This becomes cos theta. This becomes cos theta. So the two sticks gives you 2 cos theta. Okay. But the y-axis of the first stick and the y-axis of the second stick, that gets cancelled out. So all we need to do is multiply this. Okay, no, before we do that. So what was this stick then? What is this stick? Do we have a stick? Do you have any Lego blocks which would give you this stick in the first time instant? The fastest rotating stick, right? Imagine the stick that started over here and then it went really fast. This is n-1 theta, right? Which is this stick. And then n-2 theta is this stick, which is basically this stick that went n-1 and then again went n-2. So now what you're doing is you're taking a slow stick and you're adding it to the fastest stick. And that's when you add, you're canceling out the y-axis shadow and you're only left with twice the x-axis shadow. Right? That means what do you need to do? You need to make the sticks half. Because otherwise you're going to get 2 cos 0, 2 cos 1, 2 cos theta, 2 cos 2 theta, right? So you multiply this by half and you multiply this by half. Haha, and you've got cos 0, cos theta, cos 2 theta, and so forth. You've added up the x, both of these will add up and give you only the x-axis shadow. Which means this is the fastest moving stick. In other words, the fastest moving stick goes in the opposite direction of the slowest moving stick, which is the opportunity to cancel out the y-axis shadow. Right? That is why you need to add at Fn-1, you need to add this, and both of these magnitudes are half. That means when you add this rotation at F1 and you along with it you add the rotation of Fn-1, these two together cancel out y-axis shadow, and what you're left with is cos 2 pi F1 NTS. Thus, real signals are always symmetric around the center of Fs, that is Fs by 2. Right? Wherever is the center, for every frequency component on the left side, there has to be a corresponding faster frequency component on the right side. Otherwise, for real signals, the complex values on the y-axis won't cancel out. Okay. Finally, observe that all the sticks over here started at the same initial location 0, and therefore for this cos 2 pi FNTS, all phases are 0, since all sticks start at location theta equals 0. If you understand this well, many things will fall in place. Right? The only reason you need multiple frequencies is because you need to cancel out the complex part, because each rotation is a complex vector, and cos 2 pi f1 ts, f1 nts is a real signal, and real means in the x-axis shadow. And because these rotations are complex vectors, we need to eliminate those complex. So we need another complex vectors carefully, such that these two complex vectors, when they add up, their y-axis shadows are getting eliminated. So only their x-axis shadows are adding up. And therefore you make each of these complex vectors half, so that when the x-axis shadows add up, they give you 1 cos 0, 1 cos theta. Very good. Now I have a...
Wait, could you explain that last statement? All phases are 0?
Oh, all phases are 0, because remember you took the sticks and you started this stick, both these sticks at the zeroth location, right? Theta equal to 0.
Oh, so you're saying all the phases cancel out to always be 0?
No, no, no. In this case, the way you make up the cos signal is by taking the sticks and starting them at the 0th theta equal to 0 location. You could have, if for some other signal, you might have needed to start the stick at some other alpha and then move from there.
Okay.
So again, it'll become clear once we do sine.
Yeah. And then you say these are always symmetric around the center of Fs?
Fs, yes.
E divided by 2?
I mean, center of Fs is Fs divided by 2, right?
Okay.
0 to Fs, right? That's the bandwidth.
Yeah,
You
no,
have to be symmetric around the center. That center is Fs by 2.
Okay.
Quick one. Suppose I tell you xn is e to the power j2 pi f1. This is the signal. Now it's a complex signal. What should the FFT be? This is a complex signal.
So just the F1.
Exactly, just the F1. Very good, right? So all you need is just F1 at 1, and everything else is 0. What about the phase? Everything is 0.
0 everywhere? Yeah.
Exactly. Right? Because this is nothing but a rotation at F1 frequency, at frequency F1. Right? This is a complex value. You don't need to cancel anything else. So therefore, it need not be symmetric. Right? Only real signals have symmetry. Maybe we should highlight that. Okay. And now, oh, it's already pretty late. Why don't you think of this at home? How do we do sine 2 pi fnts? Remember with sine, right? We want the sine values would be sine 0 is 0, right? So if you start a stick like this, this is your e to the power j0. If you start a stick like that, and then you do e to the power j theta, which you do like that, but your first sine value, which is sine 0, is 0. But this one is equal to 1. So your first value itself is not matching.
Do we shift it by pi over 2 then?
So maybe the way to do it is you make the sine stick start here. If the sine stick starts here, then how much is the x-axis shadow?
0.
0. So you got your 0 right? But if you start the stick over there, then your next one is this. Right? So this, if If this is theta, then this is negative sine theta. But what you want is sine theta. Right? So maybe this is not the way to start. What you really need to start off as is,
How's it negative sine theta?
so this side is positive x-axis.
Mm-hmm.
That side is negative x-axis.
Oh, so we're not looking at the y. We're looking at the x shadow, not the
So
y
if
shadow.
you
Okay,
look
that
at the
makes
y
sense.
shadow, then that y shadow is cos theta, right? This value
Mhm.
is cos theta.
Okay.
Because the stick is now rotating, stick will rotate theta, right? Theta, 2 theta, 3 theta, so on. So this is theta, Utkarsh. This is the point to note. If the stick starts here, after theta, it's going to go here. This is not theta. This angle is not theta. If you started the stick here and you want to move it theta, then this is theta. If that is theta, then the x-axis projection, this value is sine theta. Right? So that will be negative sine theta. So this won't work because you want positive sine theta as your first value in your sine signal. So what do you do, guys? Someone? The idea is similar, but what can you do to make that negative positive? You start
Make the magnitude negative.
No. You start making the stick downward. And now in the second, it'll go theta. Make sense? Because now the x-axis projection is sine theta, which is what I want. But hey, we still have the original problem. There's a y-axis projection, which is cos theta. We need to cancel that out. Right? What do you do? What do you do? How do you cancel this out? Now you need to add something that you've realized by now. So what do you add to this? And you need to add a stick that is moving really fast, which is the kind of the partner for the slow moving stick. So where should that stick? What should that stick be? I think we'll end right after this. What should that stick be so that when you add that stick to this, to the left-hand side, when you add this stick, whatever we are going to draw here, to this stick, it's going to give me sine theta. Let's say it should give me 2 sine theta. Let's not worry about the magnitude. We just want to cancel off this cos 2 theta.
If you just add the other side of it like we did previously for cosine.
So you add the other side of it, which is like this, right?
Yeah, and then divide by 2.
Correct. Okay. So if you add the other side of it like this, that is, okay, then where should the stick start in this case? This is the second step, right? This is the second step. What should the first step be for the stick?
I don't know.
Pointing towards the top.
Pointing towards the top. Very good. Pointing towards the top. And then if it is moving at Fn minus 1, where should it land?
Where you just drew previously.
Exactly, where I just drew previously. This is n minus 1 theta. Make sense?
Mhm.
What is the next one? 2 theta? Sorry. 2 2 theta, where would this land? The second stick, where would it land? The faster stick?
Oh, wait, so this one is, the left one is starting on the bottom and this right one is starting on the top?
Right, correct. The left one is starting facing bottom, the right one is starting facing top. The left one goes like that, the right one does a n-1 theta turn.
But yeah, but this wasn't the case for cosine, was it?
No, this was not. Cosine, they all started at the same horizontal
Okay.
position.
Yeah. But that's fine, yeah.
Right, okay. So this at 2 theta, this guy from here, let's do a different color maybe. Blue, from here it goes here. Oops. And that is exactly n-1 theta, which gives you this. And this plus this becomes 2 sine 2 theta. Does that make sense? So what should the FFT look like? What should these two graphs look like? Sorry. F1 at half, Fn-1 at half, right? Because we want this to be half. We want this one also to be multiplied by half. But for F1, what phase should it start at? For this,
Negative pi over 2 or 3
Say that
pi
again?
over 2?
Say that again.
Wouldn't it be like negative pi over 2 or 3 pi over 2?
Negative pi over 2. And where should Fn-1 start at?
Pi over 2.
Pi over 2.
Hmm.
Everything else should be 0 because none of them have any magnitude at all. Right? Now look at sine and cos. Cos and sine have the same magnitudes, but all you do is you start the sticks at different locations and you can cancel out the x-axis projections now. Sorry, you can cancel out the complex projections differently by starting the sticks at different locations. So like cos 2 pi FNTS, you need two sticks to cancel out the complex values, but start each stick at different locations, which is phase of the frequency. Okay, we'll stop here. I'll hang back, but guys, if you want to get into machine learning, data science, signal processing, communications, if you get these things solid, this is your opportunity, guys. In many things that you will do, you spend time on this and you get it solid, everything will like fall into place like a jigsaw puzzle. Okay, so please spend time. There is a lot of value because many things have these NLP, natural language processing, graph signal processing, machine learning, deep neural networks. Many of this will have foundations here. Okay, so next class we'll finish up DSP by talking about a few other things, spectrograms and properties of DFT and Nyquist sampling, and then we are ready to get into some applications. Okay. We did good amount of math. We'll do some applications and again, come back to some amount of math. But hopefully you would agree that this math is not super dry, right? It's not like, oh, this is like spraying equations, right? There is physical meaning to many of this. Okay, I'll stop here. Thank you for attending and I'll hang back for questions that you might have.
A quick question. So we don't have lecture this Wednesday, do we?
Why not?
It's that's a holiday or the school took.
Ooh, I see. Because this is one of those spring break things.
Yeah.
Ooh, okay, if yeah, then I don't have. Yeah, sure. We won't have holiday. We'll have a holiday on Wednesday, and then we'll continue next Monday. But with these gaps, right? Please don't. Please try to stay with the material, because these things will be super valuable.
Yeah, but I mean, does that mean we'll be too far behind? Like, will we have to catch up another way, or?
No. I mean, I've accounted for some. In fact, we have a buffer in our class calendar.
Okay. All right. Thanks.
Great. Other questions?
Can I ask a question about the last example that we did?
Yes, absolutely.
Okay. I'm looking at the two components,
Hmm.
and we want only the sine component. And I'm looking at the left component. There is a negative sine component and a positive cosine component, right? In the left part?
Wait. This is stick number 1,
Yeah, stick 1.
and this is stick 2.
Yep.
Now tell me.
Okay, so I'm looking at stick 1 for EJ theta.
Right.
And here there's a negative sine component and a positive cosine component, right?
Why? Because stick 1, this is a positive sine component, right?
Wait. Traditionally, isn't sine supposed to be on the y-axis?
No. But that's not what you care, right? What we care about is the real axis. This is
Okay.
the real axis. This is the imaginary axis, right?
Okay.
Oh, I see your confusion. We want to make sine theta, real sine theta, right? So if you have a stick over here, the x-axis projection, x-axis shadow of that stick, what value will that be? If this is theta, the x-axis shadow will be sine theta,
Okay.
right? So this will correspond to what we need.
Okay. And then on the other stick, you have negative cosine shadow, right?
You have negative cos. No. Guys, let me zoom in and draw it over here. And then I'll make this very small. And let me use a different color. I start the first stick here and the other stick here. This is cool. Stick number 1 and stick number 2.
I
Now-
guess I can hold my question for now, I guess.
Okay. Now the first stick moves theta. Second stick, which is very fast. This is slow stick, very fast stick. Actually, we should make it very slow stick. Okay. So this stick moves this way, which comes to here. This stick moves this way. Sorry. Which comes to here. And this is n-1 theta. This is theta. Are you with me?
Yes.
Now what cancels? Let's do with blue. This projection x-axis shadow is sine theta. This x-axis shadow is also sine theta. This y-axis shadow is negative, or you can call it negative j cos theta. And this y-axis shadow is positive j cos theta.
That makes sense. But what still doesn't make sense to me is why is the very fast stick starting on the upper part. Like, why is the stick pointing up? Why does it have to point up? What if the stick pointed to the right or
Okay,
something?
let's do it. Let's do it. Okay. What if the stick pointed to the right? Let me keep this figure, make it really small because Utkarsh would like to have this figure. And now let's copy this figure and now zoom into it. And now let's delete. No, very fast stick we needn't have deleted. We can delete these two. Okay. So you're happy with the slow, very slow stick, right, Adil?
Yeah, I think the slow stick makes sense. I mean,
Okay.
I guess.
That's okay. You can keep thinking. Now the other stick, the very fast stick, you're saying let's start over here. Right?
Yeah.
And now this very fast stick, once you start here in one rotation, in the next time it's going to come here, right? This is n-1 theta, right? Right? So when it comes here, do you think the red stick and the blue stick will cancel the imaginary components? It won't.
Yeah, that makes sense. I can
Right?
see.
You can see, right? So
Yeah.
you have to start the fast stick in a particular position, which happens to be pointed upwards, such that after the first step, where this guy has come here, where the slow stick has come here, the first stick should be in a position where it cancels out the y-axis projection, the y-axis shadow.
Okay, that makes sense. And one final question.
Yes.
Can you go to the phase graph real quick?
Yeah.
What happens instead of calling that -90? What if you just call that 270? Is that bad?
No, that's not bad at all.
So you could have that phase at like 270 and be the same thing, right?
Sure, but I mean, this is like saying instead of -90 to +90, or instead of -180 to +180, you make it 0 to 360. That is fine.
Oh, okay.
Yeah. Totally fine. So what should I do with this? Because other people who might see the notes, let me also resize this and let me write a note that says, cannot do this.
Is that just a case of like, if you do something for one stick, you have to do it for the other, or does the first stick have to be downward orientation here?
The first stick has to be, okay, why don't you do this as an exercise? Take these two sticks and start in some other place and see if you get sine 0, 2 sine theta, or sine theta.
Oh, no. Okay. I immediately got it. Okay, I got it.
Right.
All right, I got it. Thank you.
Great. Other questions?
If we could go back to like the resolution versus field of view analogy. I guess like where I am getting confused is that at the signal that you drew at the very top of this page, the time domain signal, what I see FS as is that how well we can approximate this original signal, and then N as like a subsample, or well, not a subsample, but like a small window of that actual signal that we're taking a look over, which to me feels more like FS is resolution, and that N is just like a field of view, right? Because what I'm also getting confused at is because everything's a cycle, right? So if we only take like the first N window and we make a cycle of that, that doesn't really approximate the entire real signal anymore. So it's not like like in terms of like image resolution, right? If you decrease the resolution, it's still the same image, but over here, if you change the window size, doesn't it become a completely different signal entirely?
Okay. First, Utkarsh, let me stop the recording. Otherwise, the recording becomes super long. And since this is office hours, right?